It is my great pleasure to introduce the second speaker of this this afternoon, Professor Noemi Wolanski. Noemi is staying here for a month for the thematic semester, so she will be here for the whole next week also. So Noemi works in PDEs and free boundaries. She has a couple of remarkable results in the theory, so I could mention many, but I'll mention just a couple. There is a very nice result about the regularity of the free boundary in porous median that she proved with Luis a couple of years ago. And also, she is very well known for the singular perturbation free boundary problems, elliptic version and parabolic versions. These are very close to my heart. It influenced me a lot in my thesis at the time that I working there, and I think these works paved the way and put the theory in solid grounds for the flourishing and later developments. So Noemi, it's a pleasure to have you here, and she will be talking about asymptotic behavior for a non-local diffusion equation in domains with holds. Thanks.
Okay, thank you very much. So it's really a pleasure to be here, to spend a month in this very nice environment and to be able to talk in this conference. And I have to thank all the organizers, all the committees for this thing. And even though your introduction was mainly about free boundaries, I will not speak about free boundary problems. I will speak about something that is actually quite different from what was going on in this conference. This is an evolution equation, and the question here is asymptotics in time. Okay, so it's quite different. And while this is some ongoing work, we've been working on this for quite some time now, so I will try to make a summary of all the results, and now we understand quite well how to handle these problems, so I will try to show the methods and the questions are really common to many diffusion problems, so this could be used in other situations. This is work with Carmen Cortázar and Manuel Enriqueta from Chile and Fernando Quiroz from Spain. They are wonderful people. We are having a great time doing this work. So, where should I? Okay, here. It moved. Okay, so this is the kind of equation I am concerned with. The main difference with most of the non-local equations that were seen here is that the kernel is not singular at the origin. So this makes a lot of difference in the treatment of the problem. And so the question is the following. We have a bounded domain, H could have several components, and the problem is set in the complement of H. So in Rn minus H, we have the equation. The equation can be written actually as J convolution U minus U. In H that I will call a whole, U will be 0 for every time, and an initial condition that one can think that is 0 in the whole H. So since it is non-local, you have to prescribe, the boundary values are prescribed in the complement of the region. Actually, since the kernel J has compact support, in principle, you don't need to prescribe in the whole H unless the whole is small. We don't make any assumption on the relation between the size of the whole and the size of the support of the kernel. So the initial condition, I will only speak about non-negative solutions, even though since the problem is linear, results for non-negative solutions give you a result for any initial condition. But of course, in that case, the main final profile could vanish, and so maybe you need to go further. The initial condition is assumed to be in L1 and in L infinity because this problem doesn't have any regularizing effect, not even L1 to L infinity. So if the initial condition is not in L infinity, the solution is not bounded. And we really want to get uniform final profiles. So this was something that we had to ask for. Okay, so this you can think of as diffusion. Since this is a mean value of u around the point x, and this is telling you that the difference will the system will compensate this difference. If this is larger than u, it will go up, and if it's smaller than u, it will go down, u trying to get towards equilibrium. And the feature that is a consequence of that is that you have comparison. Okay, so this is one of the main points if you want to look at this method, these ideas in other places, is that you need comparison because we will be using barriers a lot. Okay, so this already I said. This equation has been used in models of population dynamics when there are long-range effects. It was used in phase transitions, phase field models as an equation for the phase variable, and recently also in image enhancement. So, but mainly I see it as an equation that makes sense in biology or situations like that. So the first results on asymptotics were due to Brandl, Chisani-Rossi, and Ignat and Rossi, and they concern the Cauchy problem. No whole, problem set in the whole space. What they proved is that the solution goes to 0 as t to the minus dimension over 2. So the main questions is, this is a diffusion problem. We are in the whole space here, u is 0, so u will go to 0. So the questions are, what is the rate at which it will go to 0? And then once you know what is the rate, what is the final profile? If I multiply by, in this case, t to the n over 2, what will be the limit of t to the n over 2u? What is what I will see? And when it's in the whole space, what I will see is the solution of the heat equation with the same initial condition. And the diffusivity, that is not 1, that is essentially the second momentum of the kernel. This is all that is left from the kernel from the equation, the original equation. And their proof is very different from what we do when we have a whole, because what they do is they take Fourier transform. It's one of the methods for the heat equation. If we want to see what happens when t goes to infinity, you can Fourier transform and see what happens at that level, and then bring this information back to the original one. And what they do is they Fourier transform, they find an expression for the fundamental solution. This expression, the fundamental solution, has E2 minus t times Dirac delta, the origin, plus a smooth function. Here is where you can see, for instance, that you don't have any regularizing effect. So if your initial condition has a singularity at the point, this singularity will remain forever, because the convolution with a smooth kernel would be smooth. And if your initial condition is not bounded, this part will give you that it's not bounded. But this, even though it brings all these bad properties, if you look at this is going to 0 exponentially. So if you're looking at what happens as t goes to infinity, this is not a main point. So the main point is what happens with the smooth part. And what they see is that the smooth part becomes closer and closer to the fundamental solution of the heat equation with diffusivity, this constant Q here. And this is a way in which they prove this result. And we use mainly the behavior, this decay of the fundamental solution in our study also. What happens when you have a hole? Okay, if you start looking, not only going to infinity with time, but also in space, you are far and far and far away from the hole. This hole starts to look smaller and smaller and smaller at infinity. So in the limit at infinity, this is almost a point. And if it's a point and you are not in dimension 1 at least, then you would see the same thing as you see for the heat equation. This is what you expect. So you expect to have as a final profile at infinity a solution of the heat equation, but not of the heat equation with the same initial condition, because you are losing mass through the hole. And this has to appear. But of course, this is going to infinity. If you really want to know what the profile is, this is not telling you anything. You look at the point x, and when you start looking what happens with x when t goes to infinity, you're lost. This is not telling you anything. So this information is something that you use. This is match asymptotics to bring this information to the inner region and to really find what is the final profile in the inner region. And in the inner region, close to the hole, you expect to see a stationary solution. You don't expect to see a solution of the heat equation. Okay, so this is what I'm saying here. Close to the hole, when you rescale, you expect to see a stationary solution of this Dirichlet problem. And in these 2 points, what is the final profile at infinity, and also what is the state, how are the stationary solutions of the problem? There's a big difference between dimensions 1 and 2 and dimensions larger than or equal than 3. And one of the first things that you can see as a difference between large and small dimensions is that in dimensions larger than or equal than 3, you have a remaining mass. So since mass is not going to 0, you expect to have a behavior closer to the, always at infinity, closer to what you have for the Cauchy problem. But in dimensions 1 and 2, the mass goes to 0, so this is not the behavior you expected then to have a decay of larger order. And one way in which you can see that you really have a faster decay is comparing your solution with the solution of the Cauchy problem. The solution of the Cauchy problem is positive, so it will be larger than u in the whole, and then you can compare, and you can compare at time t with a solution that coincides with u at time t over 2. Okay, so here you would have e to the t minus t over 2. The initial condition is u at time t over 2, and here the convolution between the smooth part at time t minus t over 2 and your initial condition at time t over 2. So one thing that I didn't tell you is that one feature is not just that you have comparison principle, but also that you have this control of the infinity norm. If your initial condition is bounded, then you have bound of the solution by the infinity norm of the initial condition. So this first term goes to 0 exponentially. And here, if you use that this is bounded by t to minus n over 2, here you have as a remainder the mass at time t over 2. And if the mass is going to 0, this is going to 0 faster than t2 minus n over 2. Okay. So how do you get what happens with the mass when time goes on? And this is very, very closely related to the behavior of the stationary solutions of the Dirichlet problem. So when n is larger than or equal to 3, then you have a unique stationary solution, non-negative, that goes to 1 at infinity. All the results are very similar to Laplace's equation. So just before going on, one comment is, even though what we are interested in is the asymptotics in time of the evolution problem, in order to understand it, we need to understand the asymptotics in space, x going to infinity, of the solutions of the stationary problem, of the solutions and the derivatives of the solutions of the stationary problem. But I will not have time to tell you how we get these results, okay? Existence has mainly to do with the construction of sub and super solutions of the stationary problem, and it's very easy, quite easy for n larger than or equal than 3. Now, for dimensions 1 or 2, there are no bounded stationary solutions. For dimension 2, there's one that behaves as logarithm of x at infinity. And for dimension 1, you have something like this. You are in dimension 1. Let's say this is your whole. And then you pick up any slope at plus infinity, and you will have a unique solution that will behave as b plus this times absolute value of x at plus infinity. You pick up another slope for minus infinity, and you will have a unique solution. Let's do it more dramatic. That will behave as b minus times absolute value of x at minus infinity. Okay, so this is something, this thing that you have an independent, you can get an independent behavior at plus and minus infinity, is something that holds even if this h is very small with respect to the support of the kernel. So if I look at the evolution here at this point, it will have to do with the mean value of u around this point. And this mean value could take into account what happens on this side. Okay, so you might think that maybe if what happens here, it depends on here, and what happens here depends on here, that maybe for small holes, you have some kind of symmetrization, as you do for larger dimensions. In dimensions 2 and 3, your stationary solutions at infinity are radially symmetric, almost asymptotically radially symmetric. Okay, and in one dimension, this is not true. And you can get this even with zero slope on one of the two sides. Okay, so one main feature, and this is true for any dimension, is that, okay, mass is not conserved. What's the conserved quantity here? The conserved quantity is the integral against the stationary solution. Of course, in order to make this, you need your initial condition to make this finite. So in large dimensions, it's just to be integrable, but in smaller dimensions, you have to ask for more. Okay, so this m star is the conserved quantity. This conserved quantity appears in dimensions larger than or equal than 3 as the limiting mass. Okay, the limiting mass is exactly that quantity. In dimension 2, the limiting mass goes to 0, the mass goes to 0, but when you multiply by the logarithm of time, it goes to 2 times this conserved quantity. In dimension 1, there's no clear relation between the conserved quantity and the limiting mass. What is related to the conserved quantities are the limiting first moment. Okay, so you can get, for instance, if you want the limiting first momentum, the limit of u of xt, absolute value of x in the whole line, then this will be the integral of the initial condition against the stationary solution that behaves as absolute value of x at both sides. But if you want just the limiting moment on the positive real line, the limited moment on the negative real line, you can get them as these conserved quantities. When you choose for this one, the stationary solution that will behave as absolute value of x at plus infinity and will behave as a constant at minus infinity, and the other one you have to integrate against the one that behaves as absolute value of x at minus infinity and as a constant at plus infinity. So you can get this final momentum that will enter very importantly in the final profile in terms of the initial condition in this way. Okay, so what about the decay rate? Okay, so for dimensions 3 or larger, where you have a remaining mass, you have the same asymptotic decay rate as for the Cauchy problem. In dimensions 1 and 2, the solution goes to 0 faster, as I told you before. You remember we had this inequality where you have u bounded by the exponential t minus 2. Then you have here t to the minus n over 2 times the mass at time t over 2. N over 2 in dimension 2 is 1. Mass is going as 1 over log t, so u goes as 1 over t log t. So it's faster than 1 over t, that is for the Cauchy problem, but it's not dramatic. Instead, in one dimension, we have to work more because we don't have a decay rate for the mass, not an immediate decay rate for the mass. There is one thing that we can prove is that the mass time t is controlled by the infinite norm of u at time t to the 1/2. So first decay rate that you can get is u is controlled by the solution of the Cauchy problem. The solution of the Cauchy problem goes as t to the minus 1/2. You use that, this goes as t to the minus 1/4. So m, you would say, goes as t to the minus 1/4. And you come to this inequality, but here you have t to the minus 1/2 because the dimension is 1. And here you already have minus 1/2, and here minus 1/4. So here you have something larger. So u goes actually faster than t to the minus 1/2. You come here, and the mass goes to 0 faster. So you come here, and u goes to 0 faster. So you iterate, and you get a decay of this kind. U decays as a constant times e to the minus alpha k. Alpha k is 1 minus 2 to the minus k plus 1. This holds for t larger than 2 to the k minus 1. These constants, we can prove that are bounded. And so u decays as t to the minus 1. And this is proved to be the optimal because t times u will have a non-trivial limit. And then you get this decay of the mass, t to the minus 1/2. Okay. So what are the new features that we found when we went to dimensions 1 and 2? Okay, so the first thing that we did, we worked on dimension n larger than or equal than 3. And then we said, okay, now let's complete this and go to dimensions 1 and 2. These are the easy things, okay? these were not the easy things, okay? Dimensions 1 and 2 were much harder. For instance, I just showed you that getting the right decay rate in dimension 1 was not immediate. And at the beginning, we thought that maybe it could depend on the size of the hole. Unfortunately, it did not, because it would have been a very nice result, and the result is independent of the size of the hole. But what is really more striking is that in small dimensions, you get this decay rate, okay? So for dimension 2, we say, okay, globally U decays as 1 over T log T. And this is right because T log T, U will go to a non-trivial profile at plus infinity. But if we stay in a compact set and we look at T log T U, this will go to 0. So in compact sets, it goes to 0 faster than the global decay rate. And the same thing happens in dimension 1. And one way of seeing this was the construction of super solutions. Super solutions, this we can find inside parabolas for T large. And for dimension 1, this is a super solution. If you look at this function, well, this we have to put it in order to find to make this a super solution, but this in this region is just bounded. So this is the main thing. On the boundary of this set, this is like 1 over T. So this is comparable to U in the boundary, and it's a super solution, and so this will be above U everywhere inside the parabola. For dimension 2, we construct a super solution by first constructing a super solution of the stationary problem that behaves as logarithm of x at infinity. This we already had to do in order to prove that there was a solution, a stationary solution that behaved in this way. And if you look at this, this is like log x in the boundary, and log x over log t in this boundary are comparable. So this on the boundary is like 1 over t log t. But if you look at this with x bounded, then here, if x is bounded, this goes to 0 as 1 over t to the 3/2. And this goes to 0 for x bounded as 1 over t log squared t, log t squared. Okay? So we have a different decay rate. So the idea is to do this match asymptotics to get a profile at plus infinity. Plus infinity will be outside parabolas for us, and then use this information to bring it inside the parabola. And I don't know if I put this here. I think I did it here. They put here the main problem in dimensions 1 and 2 is that the information at plus infinity is what is the limit of t u of xt, and what's the limit of t log t u of xt in dimension 2. So this will be your information, and you want to bring this information inside. But if you look at these quantities, you know that these quantities go to 0. So you don't want to look at these quantities when you come inside. So what we realized is that we had to look at these quantities. We had to rescale with these variable rescale rates that we had just found in the with these super solutions. So if you look for the limit of this quantity, then we could make the match, because this quantity is equivalent to t log tu of xt outside parabolas, and this quantity is equivalent to t log tu of xt outside parabolas in dimension 2. Okay, so what about the asymptotic profile at infinity? How can you look at this? Well, what we do, and this is something that you can do for many equations, Okay, and this has been done, for instance, for the porous medium equation, you can do it for the heat equation, for the evolutionary P-Laplace equation, is to rescale the variables. Okay, in all these equations that I just told you, you have a scaling invariance of the equation. And this comes into what you do. You rescale in such a way that you get a solution of the same equation. Here, you don't have any scaling invariance. But if you rescale parabolically, okay, this is linear, so it doesn't matter what you put here. If you rescale parabolically, this function will be a solution of a operator of this kind, where here you are rescaling your kernel in the way in which you are still with integral 1, but here you have a lambda squared. As I told you before, if you rescale, you are looking at infinity for lambda large, and your whole is becoming smaller and smaller. So what is easy to see is that if here you have a smooth function, then this operator converges to Q times the Laplacian of B. And this is another way in which one can see that the asymptotics, when you don't have a hole, has to do with the heat equation with this diffusivity. Instead of going towards the Fourier transform, you could just rescale the equation in the whole space. You will have this equation in the whole space. If U lambda is converging to some profile, then you look at the weak formulation of this equation. This operator is self-adjoint, so everything goes into the test function, and the part in the test function is going to the adjoint heat operator. And so you find that if the U lambdas are converging, then the limit has to be a solution of the heat equation. In our situation, it will be a solution outside the zero, the point 0. If you choose alpha in the definition of U lambda in such a way that the U lambdas are uniformly bounded, you're in dimensions 2 or larger, then you will have U bounded, and then it will be a solution of the heat equation everywhere. So you expect solution of the heat equation everywhere. And if you can determine the initial condition, you determine U completely. And if this is independent of the sequence lambda n going to 0, then because this will actually hold on sequences, it will be a compactness argument, then it will hold for every lambda going to 0, okay? So what's exactly the relation between this limit and the asymptotic profile at infinity? Well, suppose that we prove that U lambda converges to this profile U as lambda goes to infinity, uniformly on compact sets of Rn minus 0. So you look, for instance, at this annulus, Br minus B delta, R delta arbitrary. You have to stay far from the origin in time. You have to stay with T controlled also, but in particular, you look at time T equal 1. Okay, and you know that this will go to 0 uniformly. Okay, so what is U lambda at time 1? Is lambda to the alpha U of lambda psi lambda squared. So, okay, rename this. This is lambda squared is your time, and this is your variable, x. Okay, so the U lambda psi 1 will be lambda to the alpha will be t to the alpha over 2, and then you have U of xt. And if you call f this profile, then this will be the profile at x over square root t. So you translate, and it tells you that as t goes to infinity, the supremum of t to the alpha over 2 times the difference between u and this profile goes to 0 uniformly in these regions, two parabolas that go. It's integrable? No. No. Something else that will give you, for instance, the decay t to the minus n over 2 that you have for the good part of the fundamental solution. So at least you need integral 1, let's say, non-negative, radially symmetric, and finite second moment. Okay? With that, you can get this. For other things, you might use the compact support. Okay, so as I tell you before, we have to get the conversions of u lambda to u. In all the examples that I told you, the u lambdas were solutions, bounded solutions of an equation, heat equation, porous media, for instance, and you had a regularizing effect, and so you get the compactness for free. Okay, but here we don't have a regularizing effect, so in order to get compactness, what do we do? Okay, we realize, okay, this is, some things are much easier, some things you don't have, but you say, what will I do? I don't have this. Well, but you have something that you don't have in the classical setting. Is even though you are with a problem in the complement of a set H, you can see your solutions as being solutions of a Cauchy problem, a problem set in the whole space. And this is the problem. Instead of having ut minus lu equal to 0 in the complement and u equals 0 inside, you realize that globally you have this equation. Okay, why is this? Here you are subtracting j convolution u. Oh, here there's a minus missing. Okay, it should be minus. So you have ut minus j convolution u plus u. If you are in the whole, the convolutions will go and you will have ut plus u equal to 0. So you have initial condition is 0 and ut plus u is 0, so u is 0. And the other way around, if u was 0, ut plus u is 0. So inside the whole, the equation holds. Outside the whole, this is not there, it's 0. So in this way, since this is a solution of a Cauchy problem, we can use the fundamental solution, variations of constants formula, and get a representation formula for the solution. And in the representation formula, you have a very bad term that comes from here but goes to 0. So you don't care about this term in the compactness argument. Then you have another term that is very bad, but if you are outside the origin, vanishes. And then you're left with two terms where you only have convolutions in space or space-time with a smooth kernel. And so you can prove for those terms, you can get bounds of the derivatives, and you need some information on the behavior of this kernel, point-wise information, not just how it goes to 0. And what we get, again, with more PDE style. W is a solution of an equation, and the derivatives are solutions of an equation, and we construct barriers, and in this way we get point-wise estimates. Okay, so what do we get? For n larger than or equal than 3, we know that the alpha has to be n. We can prove that the final file has as initial condition the final mass times the delta Dirac function at the origin. So your final profile is m star times the fundamental solution the fundamental solution is invariant under this scaling. So if we go back to the result that we had before, it's just the final profile at infinity will be just m star times gamma. Okay, so in case n equals 2, if we want u lambda to be bounded away from the origin in time, then we have to multiply here, remember, by t log t. So this will be our lambda squared log lambda. And if you look at the integral of this function, it takes this form. And so this will converge to m star, the conserved quantity. And again, we prove that the initial profile is this m star times gamma sub q. We come back to our analysis, going to the variables x and t. This function is not invariant under this scaling. It's invariant if I don't put log lambda. This is why the log t remains here. Or if I want to put t log t outside, I had to divide by log t here. So the difference between dimensions larger than 3 and dimension 2 is this is a different order, but also there's a small change in the final profile. It's not the fundamental solution, but the fundamental solution divided by log t. No, not a striking change with respect to large dimensions. For one dimension, the difference is much more profound. So even, as I told you before, with a very small hole and interaction between the two sides, the profile at infinity is in general not radially symmetric, as in the other cases. And what we find when we do this analysis, for instance, is you get a solution of the heat equation for x positive and for x negative, but not across x equals 0, but you can prove that the final profile vanishes at the x equals 0. So what you get actually for the final profile is two dipole solutions. The dipole solutions are derivatives of fundamental solutions. Okay, so there's one on the positive real line and one on the negative real line. And the slopes of these dipole solutions are the final first momenta on the positive real line and the final first momenta on the negative real line. But this we already could determine in terms of the initial condition by these conserved quantities. Okay. So we have this result, this kind of conversions. This was the rescaling. The dipole solutions are invariant under this rescaling, so these dipole solutions is what you see in the final profile, as final profiles, and you can write them more or less in the same way for x positive and x negative if you write them in terms of the fundamental solution, and you have an absolute value of x over qt times the fundamental solution, but with different slopes at plus and minus infinity. Okay, so what about the inner region? Okay, so we have this behavior for outside parabolas, and now for some delta, for some parabola, we would like to get the behavior, the final profile inside. In dimension 3 and larger, is, as I told you before, it's the same limit. I know what is the limit of t to the n over 2u of xt outside parabolas, and I want to get this limit inside parabolas. But as I told you before, for dimensions 2 and 3, these are the quantities that I want to get. So let's start with dimension 3 and larger, because this is the simplest one, and it's the idea, okay, of everything. So since this is a non-local equation, boundary behavior, boundary conditions have to be given in a region. And here, I'm using that the kernel has compact support. So at this point, it's important that it has compact support. So I'm only concerned on the final profile in this kind of regions between two parabolas, and not the whole region outside parabolas, okay? And so I rewrite what I have in this region. This is the final profile at infinity, okay? So U of xt has as final profile m star gamma sub q. But I need the stationary solution to appear somehow, because I want this to appear in the final profile. It has to appear in the final profile inside the parabolas. And in this case, phi goes to 1 at infinity. So in this region, it's going to 1 uniformly. So I can put it here. And I would still can say that in this region, U of xt converges to this function, and phi appears. In which way it converges? This difference, even when multiplied by t to the n over 2, becomes small if t is large. So this difference is bounded by epsilon t to the minus n over 2, given any epsilon if t is large. And so I have this bound from below and a similar bound with plus from above. I continue from below. I'm in this region. In this region, this function is equivalent to 1 over t, equivalent to t to the minus n over 2. So I can replace this by a constant times this function. So I get as a lower bound 1 minus a constant that depends on this delta, m star phi of x gamma sub q, and with a similar analysis, I get this bound from above. Okay, so essentially, this is what I've written here. There's a profile, and u is between two multiples of the profile, very close to epsilon in this region if t is large. Now, for future computations, getting this function inside the non-local operator becomes involved. So instead of this function, we will put the w, the good part of the fundamental solution, because these two are equivalent. The difference, even multiplied by t to the n over 2, goes to 0. And I have this inequality. So I really would like to get something like this inside the parabola for t large. This would tell me that this would be the final profile, or the same thing, that this is the final profile. But of course, I cannot just say, okay, this happens here, so it will happen inside, because these are not super and sub-solutions of the equation. So what we do is, well, we modify, we perturb this final with our candidate to final profiles. We perturb with some function in such a way that when we add, let's say, we have a super solution of the equation. When we subtract, we have a sub-solution of the equation. But this is of a higher order. So this multiplied by t to the n over 2 goes to 0 inside the parabola. So in the limit, as t goes to infinity, this will disappear. Okay, in order to analyze and get this construction, I also need some behavior of the gradient of the stationary solution, and not just what happens or how the stationary solution converges to 1 at infinity. And this is the final result in dimensions 3 and larger. This is the final profile. So let's say what happens in dimension 2. Again, we need to make this function phi of x appear in the final profile at infinity in order to bring it towards the inner region. So we need something that goes to 1 related to phi. And what goes to 1 related to phi is phi over log x. And in this region, log x is equivalent to 1/2 log t. So this quantity 2 phi of x over log t is going to 1. So in the final profile, the final profile was 2m star gamma sub q over 1 over log t. So I introduce this phi of x over log 2 phi of x over log t. I have this final profile, and the order of conversions was 1 over t log t. So these would be my candidates to final profiles. And again, I replace gamma sub q by w. This will be my candidate to final profile. But I want to do more or less the same thing, to construct a super solution and a sub-solution that will essentially be my final profile when t goes to infinity, even when multiplied by the rate of decay. And in dimension 2, we cannot do it. There's this, it's complicated. And so what we have to do is a more complicated super solution with 2 terms and so on. Doesn't matter. It's very technical. The main problem in dimension 2 was the construction of super solutions. But we get this final profile with this order of conversions. In dimension 1, instead, the construction of super solutions is easier. The main point is we had one profile at plus infinity and one profile at minus infinity. If I want to have a phi appear in my behavior at infinity to being inside, what is the profile that the stationary solution that I have to put? Okay, what I have to put here is the one that behaves as m1 plus absolute value of x at infinity and m1 minus absolute value of x at minus infinity. This stationary solution will give me at the same time the behavior at plus and at minus infinity. And so this is my candidate to be the final profile. So we perform similar computations, and we get this as final profile with this order. What was the complication here in one dimension is that in order to see in order to construct super and sub solutions, we needed more information on the behavior of the stationary solution at infinity than what we needed for more dimensions. So we needed to know how the derivatives were close to the slopes and how the second derivatives were going to 0 in order to be able to construct the barriers. You want to ask me something? Yeah, this is the profile, and this is the order. This is non-trivial. This is exactly, if you look, this is more or less, let's say, at infinity is like absolute value of x over t. So this will give you and this is like 1 over t to the 1/2. So you have, this has exactly this order. Okay, so if you concentrate on compact sets in order to see what you get in every situation a multiple of the stationary solution, okay? So this is the multiple that you get in dimensions 3 and larger. In compact sets with this order, you get this in dimension 2. And with this order, you get this function in dimension 1, okay? So what about what happens outside parabolas? Because everything I said was inside large parabolas. Well, outside if you go with x over square root t to infinity, then what happens with the initial condition is starts to make, to decide what is the asymptotic. So you don't have a clear asymptotics, but what we know is that actually these things go to 0 with the order. For instance, t to the n over 2 u of xt will go to 0 when x over square root t go to infinity and so on. So actually these things are global. In dimension 1, for the heat equation, we didn't find this result, okay? So what do I mean about this result? The fact that on compact sets, t to the 3/2 u is converging to something, okay? The thing is that for the heat equation, this limit was just the dipole. So everybody was happy to know that the limiting profile was a dipole solution. But it was a dipole, u of xt was going to the dipole. But if you are in compact sets, even for the heat equation, tu of xt is going to 0. So if you want to really say what happens and find what is the right decay rate, this was not done, so we just wrote a note about this. And we are using the same idea to get the final profiles for the porous medium equation, because something similar happens with the porous medium equation. The results that are given as global results are not good for dimensions 1 and 2. For dimension 1 and 2, the decay rate on compact sets is larger than the global decay rate, so they don't know what is, it's not written what is the final profile. And the final profile in the case of the porous medium equation is not just the same as the one at infinity, but with a different decay rate as for the heat equation. It's something different. Okay, so we are finishing this. That is, of course, much more complicated because the perturbations that we have to do are linear perturbations, not just linear perturbations. So it's more complicated. Okay, so thank you very much.
Thanks, Noemi, for the nice talk. So before we go to any questions, let me just do a quick but important addendum to my introduction that I did in the beginning. So I mentioned this nice work with Noemi about flame propagation in collaboration with Luis. And I forgot to mention Claudia, of course, Claudia Lederman from University of Buenos Aires.